Welcome back. In this second part of our demo series, we'll focus on constructing the features xvars and target variable yvar for our model. Let's start by defining the target variable. The target variable is residual returns over an n-day horizon. Formally, if y sub t is the target for day t, the target variable is the sum of daily returns from day t plus 2 to day t plus n plus 1. For example, on January 2nd, if we want to compute 5-day future returns, we sum daily returns from January 6th through January 9th, skipping January 5th to allow for data lag and trade execution. The same rolling logic applies for subsequent days. Even though signals are ultimately assessed on a one-day future return, we use a multi-day horizon for the target to smooth out volatility. In this section, we'll build our X variables, or features, that serve as inputs to our model. This involves transforming the raw datasets into useful features. The goal is to create two data frames, X, Y train. This is used to train our model, contains both features and the target variable. And X predict, which is used for generating out-of-sample predictions with the trained model. There are some constraints on the form of our predictions, which in turn constrain our xvars. First, our predictions must be causal. In other words, there must not be any look-ahead bias in our data. All predictions on date t must depend only on the data available on or before that same date. This is very important because, otherwise, we can't use the resulting strategy in live trading. Next, the primary keys of our predictions are date and quick code. This means their combination must be unique, so there should be no duplicate date and quick code pairs. This also means we can't have nans in those columns. We also don't allow any missing dates, meaning we don't allow any dates for which there are no predictions. Finally, we require at least 1,000 predictions per date. In this segment, we'll explore some practical guidelines for creating robust, high-quality features. First, it's essential to maintain causality in your dataset, meaning there must be no look-ahead bias. All features you use on day t should only depend on data that's available on or before day t. If your model ever needs data from a future date, like day t plus 1, to make a prediction for day t, you've introduced look-ahead bias, and your results won't be valid for real-world trading. The provided scripts already manages most of these date calculations, so this shouldn't be a problem by default. Next, we want our features to be stationary. That is, their statistical properties, like mean and variance, shouldn't shift drastically over time. If the distribution changes too much, your model's training assumptions may not hold in the future. Normalization or standardization can help achieve stationarity by putting features on a consistent scale. We also want a diverse set of features. Having many features is good, but it's even better if they're not too correlated with each other. Consider using cross-sectional, rolling, or other transformations to capture different market behaviors and signals. While models like light GBM are fairly robust to collinear features, it never hurts to reduce redundancy where possible. Additionally, our features should be dense, meaning they shouldn't have a lot of missing values or invalid entries like nans or infinities. The more complete and clean your data, the better your model will perform. And finally, when possible, aim to make your features meaningful or interpretable. Drawing on your market knowledge or common sense to create features can often lead to better insights and potentially better performance than purely abstract transformations. By following these guidelines, avoiding look-ahead bias, ensuring stationarity, fostering diversity, maintaining density, and striving for interpretability, you'll lay a strong foundation for building effective models and, ultimately, generating reliable trading signals. Now that we've covered the key principles for effective feature engineering, let's dive into the practical steps for building your X variables. This forms the core task of the Datathon, transforming raw data into meaningful causal features that can power your model. To make this process smoother, we've provided helper scripts and a Jupyter notebook called Alpha Generator. These tools are designed to guide you through everything from data cleaning and merging to applying transformations and generating feature columns. By following the documented workflows, you can focus on crafting your features. Remember, your ultimate goal is to produce two data frames, one for training, XY_train, which contains your features alongside the target variable, and another for generating predictions, XPredict. In the following segments, we'll walk through each step in detail, ensuring you have a clear roadmap for building a robust feature set. There are multiple scripts available to help you construct your model. Most of your work will happen in the Alpha Generator notebook, where you'll build the target variable, Section 3, and engineer your features, Section 4. But let's start with the foundational setup in Sections 1 and 2. Section 1.1 contains all the required packages and functions. This section imports all the packages and utility functions you'll need. It's essentially your toolkit for the competition. Everything from data manipulation libraries to custom classes. Section 1.2 has all the dataset paths. Here, you'll find the paths to every dataset available for the Datathon, defined in the init.py file inside the PyAlpha directory. If you ever need more information about a dataset, you will be able to find them in Data Store. Section 1.3 discuss the pre-built functions. This is where we introduce some of the most crucial helper functions. One standout is the dates class, used in the notebook as dates_obj, found in utils.py. Its date range function, for example, returns all trading days between any two dates you specify, perfect for slicing your data without accidentally reaching into the future. You'll also see a read data function, which streamlines loading datasets by letting you specify a path, a date range, and optional parameters like columns or mInDate. This is particularly useful if a dataset only starts at a certain time. Participants also have access to transforms.py under PyAlpha. There are two types of transforms: cross-sectional and time series, or rolling transforms. Cross-sectional transforms modify a stock's feature by considering the values of other stocks on the same day. These transforms group the rows by date and apply the transformation to all stocks available for each date. This prevents values from other potentially future dates from affecting the current date. Some examples include demean by date, demedian by date, z-score by date, and rank by date. The second type of transform is time series or rolling transforms, which modify a stock's feature by considering its past values over a fixed window. These transforms first sort the data frame by date to prevent look-ahead bias, group it by quick code, and then apply the transformation on a rolling basis for each group. Some examples of rolling transforms include rolling mean, rolling median, and rolling z-score. These require a window argument, the number of days in the past the transform looks at, and an optional argument mine periods to set the minimum number of observations required for a valid transformation. Participants are highly encouraged to get familiarized with these functions before the actual event, as these functions are very useful for feature engineering. Feel free to combine and customize these transforms as much as you like. You can even create brand new ones if you have a specialized approach in mind. Moving on to Section 2, this part automatically determines the date ranges for training and prediction based on a few key inputs. Pred start date, when you want your predictions to begin. Pred end date, when you want your predictions to end. Train look back years, how many years of historical data you'll use for training. Holding period, the number of days over which you're predicting future returns. For example, 5 days. X days look back, additional days of data needed if you apply rolling or window-based transformations. Here's a quick example of how it all works. Suppose you want to generate predictions for January 2018, and your model uses a 2-year training window with a 5-day holding period. The notebook automatically shifts your training data back by 5 days to avoid look-ahead bias, skipping the last 5 days of December so you don't accidentally include future returns. In practice, that means Pred start date might be January 1st, 2018. Pred end date might be January 31st, 2018. Train start date then becomes December 22nd, 2015. Train end date becomes December 21st, 2017. This calculation is handled by the Identify Adjusted Train Dates function in utils. If you also apply rolling transforms, say a 60-day rolling average, passing X days look back equal to 60 will instruct the script will include an extra 60 days of data before the training window to ensure those rolling calculations aren't full of nans in the initial days. Now that we've covered sections 1 and 2, setting up our data paths, date logic, and foundational scripts, it's time to dive into the heart of the notebook, building the X and Y variables. We'll begin with the Y variable, which represents the target or future returns we're trying to predict. There are two main ways to handle this in the Alpha Generator notebook. First, participants can use the pre-computed residual returns. If the holding period you're interested in has already been computed, you can simply read in the quick residual returns files. These files come with certain forward windows pre-calculated, so if one matches your needs, you're good to go. Another option is to compute your own future cumulative returns. If you need a holding period that isn't already available in the residual returns files, we've provided a function called Compute Future Cumulative Returns. By passing in your chosen holding period, you can generate custom Y variables that align with your exact strategy. Choosing between these methods depends on your specific requirements. If you can work with the existing forward windows, you'll save time. If not, the custom approach ensures you're never limited by what's pre-computed. Now we arrive at the most crucial part of the notebook, Section 4, where you'll construct the variables that serve as inputs to your model. In this step, we'll bring together multiple datasets, apply any transformations you need, and ensure the final data structure is both reliable and consistent. Step 1 is to read the datasets. Several datasets have been made available for this Datathon. You can use all of them or just a subset, depending on your strategy. To load a dataset, call the read data function we introduced back in section 1.3. Remember to read univ path first and merge all other datasets to this file. This file contains the stock universe for this Datathon. Keep in mind, each dataset might have different unique keys. Don't assume that every dataset automatically aligns on date and quick code out of the box. Also, some datasets don't start on the very first day of your in-sample training period. If that's the case, specify the min date parameter so the function knows when your data actually begins. Step 2 is to merge the datasets into x_df. Once you've read each dataset, the next step is to merge them into a single data frame we'll refer to as xdf. Here, it's important to ensure you don't violate any constraints mentioned earlier, such as avoiding duplicate, date, quick code, keys, maintaining causality, and managing missing values. As a best practice, it's wise to double-check for any duplicates or unexpected overlaps before you move on. Step 3 is the most important part, where participants will likely spend the majority of their time. This step is where transforms are applied to features in x_df to get useful features. Predefined transforms are available to participants and can be found in the transforms.py file as discussed earlier. Again, make sure that none of the constraints are violated, and take care not to read future data or introduce duplicate keys in your transforms. As you wrap up feature engineering, remember that your final set of X variables should consist entirely of numeric values. It's a good idea to double-check your transformed data for any irregularities, like outliers, missing values, or unexpected data distributions, before handing it off to your model. Once you're confident in the quality of your features, you'll be ready to train your model. We'll explore that process in the next video, where we'll dive into fitting the model, generating predictions, and ultimately evaluating how well those predictions perform in a real-world trading scenario.